Hello and welcome to this video on fluorescence. Fluorescence, or fluorescence if you're using civilized English, is the emission of light, or more broadly, electromagnetic radiation from a substance after it has been stimulated by the introduction of energy. While technically sound, this definition can be simplified to when you put energy into a thing, it shines. This is why and how glow-in-the-dark paint works to some extent. The key to both definitions is that the light you put into the substance is able to power the emission of a new light. However, like animals, all light is equal, but some is more equal than others. That is to say, the shorter excitation wavelength is able to stimulate the release of the lower power or energy of a longer wavelength of light. This is why, despite it seeming like energy in equal amounts goes in and comes out, there is in fact a change in the total energy as a result of fluorescence. On a single event scale, the change is minuscule. On a universal scale, it is considerably less so. This is why it's contributing to the eventual heat death of the universe. In order for fluorescence to happen, certain criteria must be met. First, we start with the idea that you must have a thing. Generally speaking, this is going to be a small molecule. When the molecule, atom, or anything else is in a high energy state, that is, when the power or stimulus is being given or put into the thing itself, nothing is going to happen, and that's simply because, well, you're generating that power, it's not trying to discharge it. However, once it starts going into the lower energy state, this is when it begins to emit light in the form of photons. This is, generally speaking, what's going to happen, and it's the process of going from that high energy state to a low energy state that creates the phenomena of fluorescence. In a manner of speaking, you can compare this to the way a battery functions. That is, by having the high energy state of the battery, it sends power down to the low energy state LED, and because the LED then gets power, it's able to discharge that, and the discharge process allows it to emit light. It's a slightly different scenario, but it's fundamentally the same concept, just executed in a different manner. The key distinction, other than the nature of how we're getting light, is the fluorescent lifetime. That is, how long the molecule will stay in the excited state before it emits a photon. Generally speaking, this is going to follow first-order kinetics. This is where the concentration of excitement or power in the molecule at its initial point versus how far it decays or how quickly that power is used. This means you can get an idea of how much initial charge you put in versus how long that charge will remain functional. As a general rule, the decay will be an exponential function. This means that you initially get a large drop-off followed by a much lower drop-off towards the end of its energy. This again is in some ways very similar to how a lithium battery works, except the lithium battery is the inverse. You get a very slow drop-off in power in a lithium battery, but at the end you get a very sudden drop-off. Of course, as with most things, it's not as simple as just how much power and how quickly it decays. The use of that power does follow a series of rules that will tell you how long a thing will fluoresce. The first being Cash's rule. This will tell you the quantum yield of luminescence dependent of any kind of excitation. This means that no matter what power you put into it, this will tell you how much luminescence can be generated. Although this is going to obviously be one of the lower level rules, since once you start adding energy into it, things change drastically. And this is because, well, most molecules will never get to the fluorescent stage before they actually get to this rule. That means this rule comes into play after all of the other fluorescence has occurred, or before you start energizing the thing itself. This leads us to the first instance that's more practical, or at least, in terms of something you can appreciate visually, the more useful rule. This is the mirror image rule. It fundamentally comes down to the idea that the absorption spectra and the emission spectra will shift just enough that you get a rough mirror image of each other. Pretty much you get a very narrow side and a long tail on the other. And of course, the narrow sides are going to face each other given that this is a mirror. Ideally, this means you should be able to get the emission spectrum to be a perfect match to the other. For most people, the obvious example of this is going to be something like a highlighter. The highlighter is useful as well. It does exactly this phenomena. The amount of power going in and the amount of visible light in the form of phosphorescence coming out is pretty much a perfect mirror. And next we have is the Stokes shift. Now the Stokes shift is a part of how we know that energy going in and energy coming out are different to start with, but more importantly that it's going from a shorter wavelength to a longer wavelength. The Stokes shift pretty much points out that the energy loss between both time of photons being absorbed and emissions of new photons leads to that difference in wavelengths, and to a certain extent will depend very much on the fluorophore, or the compound that is giving the phosphorescence or fluorescence. There is two important caveats to the Stokes shift that point out important lessons to take away from it. First is that because you are seeing non-radioactive decay, that is, the molecule itself is not breaking down, you get a reduction in the level of excitation, but not a permanent reduction. And this means that when the photon is emitted, the molecule remains in a reduced level of excitation. This is described as a higher vibrational level of the ground state. When you re-energize or recharge your fluorescent compound, you're able to take it back to that earlier state and fundamentally reset it. This leads us to why fluorescence is important, and other than things that glow in the dark, it can be very powerful as a research tool. Fluorescence spectroscopy is one of these. That is, if you are able to have a fluorescence detector and you run your blank sample through and then your test samples through, you can establish whether or not the thing fluoresces, and from that you can establish how much of something is in a sample, if you're basing it on fluorescence. This is particularly useful if you have, for example, decided to tag something, that is by adding a fluorescent molecule to it somehow. This can be done through, for example, fish, or fluorescence in situ hybridization, by a native fluorescence in a compound, or by using something like an antibody with a fluorescent molecule attached to it. All of these allow for detection and quantification. You can also use it, for example, if you are looking at something like trying to insert something into an organism. For example, if you want to scan the body for particular locations and track them, fluorescence can do this to some extent. Or you might use it in terms of forensics to see if you can find the spread and location of certain chemicals or DNA or something similar to that, where, again, through something like antibodies and a black light, you might be able to find where semen is. If CSI or SEVU is anything to go by, this is far more common than you'd think in reality. A somewhat common student experiment that uses this same idea is to take the green fluorescent protein, otherwise called GFP, and insert it into bacterium or other microorganisms due to genetic modification, and then grow them on a petri plate along with an antibiotic that's resistance is included with the green fluorescent protein. Then only those that survive and will shine from the green fluorescent protein have successfully been transformed. This is just one example, and along with the others you can see how fluorescence can be used, particularly if you think of the idea of wanting to select for particular traits, and so by being able to shine the right wavelength of light onto something and then get the right excitation wavelength out of it, you know that only that thing you want is present. At the same time, you can to a certain degree be able to analyze things. For example, the spectroscopy or even chromatography can use exactly the same ideas. This is why fluorescence is a useful tool based on how it functions. Not just is it reliable and predictable, but it's also relatively convenient. Admittedly, depending on what you need to do, that convenience can be significantly less than convenient, but for most applications it is very efficient, very effective, and reliable. That means that you can consider it a powerful tool, if it works as intended, and unfortunately that's not always the case. Thank you for watching this video. If you found it interesting, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions you have below.